Hello. Hi guys, good morning. Welcome back to the new video. In this, we will see the problem. Find beautiful indices in the given array 2. Primarily, we'll be focusing on the KMP algorithm, which is a string matching algorithm. So we have string matching algorithm as two algorithms, Rabin-Karp and KMP. Now, why we use KMP is, although learning KMP is a bit tricky rather than Rabin-Karp, but the code is just of 4 or 5 lines. That's it. While Rabin-Karp code plus handling of that code can be a bit long. That's the reason we will discuss Rabin-Karp as a string matching algorithm for this problem. We will see from very scratch what is Rabin-Karp, how it is used, entirely on how we derive the formula, and ultimately we'll also see the time complexity of Rabin-Karp with a proof of all of that also, because many people just assume that it is O of n plus m, but you have a specific proof why it is O of n plus m. Now the problem is very simple. It just says that we are given a, now we will take a reference of this problem so as to understand how and where Rabin-Karp or KMP can be applied, as in a string matching algorithm can be applied where else. So you are given a 0 index string s, a string a, a string b, and an integer k. So I have a string s, string a, string b. You will see a string s, string a, string b, and an integer k. Now what my task primarily is, I can go and check for all the i's. Now I just ultimately am saying that okay, my match, the string a should match my s. Then where it is matching, that index I will store. Okay, that index is a 16 for me. This index is a 16 index, but it is also matching here. So I also have a 33 index. String b, it can also be matching in string s. Okay, yeah, you can see squirrel is matching. So for sure I know that okay, at index 4 I am matching that. Okay, so at index 4 I am matching, and also squirrel you will see is matching here also. So at index 18 also I am matching with this. Now you figured out that okay, string a, again you saw before even reading, string a is matching in string s, string b is matching in string s. At what all places it is matching, this is what you have to figure out. So ultimately when you have figured out this thing, then you can say that okay, my string a is matching at 1633 and my string b is matching at 4 and 18. I have to just give me all such indexes of string a, which are actually, if I can find any index, which is let's say j, this is index let's say I, if I can find any index j, which I can say okay, I minus j should be less than equal to my 15. So for this index 16 in the entire array for my b vector, let's say b vector, I should be able to find any of such closest number to my 16 such that, bhaiya, why closest you want? Because ultimately I want that it should be less than equal to k. So I would want, okay, if I is 16, I would want something which is as close to 16 as possible. It can be either 15, 14, anything which is as close. It can be even 17, 18 like that. Now my prime aim has become that I will just figure out these values, which is for my string a, I'll just figure out my 16 and 13, 16 and 33, and for my string b, I will figure out my 4 and 11. When I have figured this out, then it's super simple that I will have 16. I will go and do search on my this array, let's say b, and I will find out nearest number to 16. It can be either 17, 4, which is okay, nearest number either higher or lower, but nearest number I will find out in this array of indexes, and then if it is less than equals to k, then great, which means I'll just find out for the just higher number and just lower number than 16, and this is what I'll perform for all of these elements. Now just a big optimization at the top of a head would have been okay, I'll just search if I want 16, so nearest number I'll search for either higher or lower by just doing a bind search, lower bound, upper bound. That is how I can simply find it. But now comes the main task, is how will you even figure out this particular specific value, which is indexes, where it is matching, because in the worst case it can match entirely and your string sa is actually very big. Now in case of string matching comes is your KMP or Rabin-Karp. Now let's see that what this string matching actually means and how this can be done. So ultimately KMP says, again, you will just hear the word longest prefix which matches suffix. That is, but I'll say KMP simply says that longest prefix which is actually matching with your current string which you want to match. So now with KMP, you know that you will have two strings and you will be easily able to figure out what matches with what. But before going that, let's see what other people tell about KMP. They just say that, okay, longest prefix that matches suffix. That's what other people say. But I'll say longest prefix that matches my current string which I want to match. What I mean by that is, if I want to make my LPS array, what is bhaiya LPS array? LPS is longest prefix which matches suffix. This is the LPS array which we will name because by default it is how it is named. So we have a string S, but bhaiya, my ultimate aim was to match two different strings. Why are you just showing me LPS thingy, which means you are just showing me longest prefix which matches suffix in one string? How it is even helpful? Hold on. Just understand that what this thing actually means. This means is that, okay, if I have a string S, I will compute an LPS array. Now, how this LPS array is computed is, you will just start off and let's say you are here, A. Okay, you are again. Whenever I say you are here, always imagine everything in the left. Forget even everything in the right. Forget everything in the right? Okay, cool, great. Now, you are at this location A. What is the length of the prefix which matches you? There's nothing previously, so for sure nothing is there. Now let's say you are at this index. What is the, again, forget everything after this, again, remember that. Okay, cool. Now when you are at this location, so anything, okay, A is matching this A. So longest prefix which is matching me right now is actually a A only. So length is 1. One length is matching. Bhaiya, it is still unclear. No worries. Let's say if I have a B. Prefix start itself with the A itself. So there is no prefix which is matching. Okay, cool, no worries. If I have a A, no worries. So you will see that A. Oh yeah, A is matching bhaiya. So for sure, yeah, A is there. So length is 1, which is matching. Now comes interesting part. Again a A comes. Now you will say, bhaiya, okay, again I can see that A is matching with A. So length should have been 1. But I'll say, wait, I am saying that your string is ending here itself. So longest prefix, AA, let's say longest prefix which matches suffix. So your suffix here, longest suffix is, it can be this long suffix, but I'll say it cannot be entire string. So it can be this A, it can be this AA, it can be this BAA, it can be this ABAA, and that's it. These are the suffixes of my string up till here. Now I'm asking you, what is the longest suffix which is matching? So you will try for ABAA. ABAA, is it matching? Nah. Okay, cool, then it is gone. I'll try for BAA. BAA, is it matching? Nah. Cool, no worries. I'll try for AA. Is it matching? AA. Yeah, it is matching. So this is the longest suffix which is matching my prefix. That is the reason my answer is 2. Okay, cool. So that's the reason why this term is called as longest prefix which matches suffix, because I am assuming that my string is ending right here and then I am computing this value. So so is the name LPS. Now comes the C. Okay, we have no C, so for sure it's gone. Then comes the A. We have 1A, so answer is 1. Then comes AA. Okay, because again ending at this value. AA is the prefix. Okay, AA, length of 2 I have. Okay, length of 2 is there. So this is saying, okay, length is actually there. Now if I have a B, yeah, AAB, yeah, that is true. Length is 3. If I have again a A, okay, AABA, yeah, length is 4. That is true, because you will see AABA, it is matching with this. Okay, cool. Now if I am at here, now I'll try for saying AABAA. It's the longest suffix which I'm trying to match with my prefix. Yeah, it is matching. AABAA. Cool. Again, go ahead. Then I'll try for having a D. I'll try for everything, but nothing will work. D itself cannot work here. So for sure, length is 0, which is matching. This is what it means by longest prefix which matches suffix. But bhaiya, again, the question was, how will you match two different strings? So now I'll say, to match two different strings, what I'll do is, okay, I know this is my one string, which I need to know or match in my this above string. Now the brute force way for sure you would have known is that you will try for every, okay, you will try for this string to match with every of the index. If this is matching, you will try for all up till the end if it is matching or not. If it doesn't, then you go to next index, then again try for the entire pattern matching, then next index, again map entire pattern matching. This is how a normal O of n square brute force matching would work. But again, we cannot do that. We want a more optimized matching. So what we will do is we will apply, let's say this is a pattern and this is a main string which we want to match. So we will just make a new string as pattern hash my new string s. Now what will helpful with this is, you will see that you will make an LPS array. Now with this LPS array, what these number will indicate? These number will indicate, again, you have put a hash. So for sure, no pattern will anyway will match after this, right? So no prefix will anyway match after this. So it is kind of, you are saying longest suffix which matches your prefix, and prefix is a pattern. So longest suffix which matches your pattern. So right now at this point, up to whenever I say up at this point, I mean only up till back. For afterwards, forget everything. So at this point, I will say longest suffix which matches my pattern, 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 and so on and so forth. Now bhaiya, okay, let's imagine, and again it's a black box for you, that you will just have a pattern, you will have a string s, you will just put a pattern, you will put a hash, you will put a string s, then you have a pattern, hash and string s, and you can just put any character which is, you know, that will not be in your p and s, which means pattern and string. Now when this is there, so you will for sure know that all these values of LPS will show you that longest matching with your pattern. Now ultimately, if you want your entire pattern to match, you know the pattern length is 4. Your LPS length says longest prefix which matches suffix. So you will try to find the 4 length. Okay, the 4 length is here, which means this 4 indicates that at this point my suffix is matching my prefix, and this is what we wanted. So ultimately, when we have, again, it's a black box for you right now, that firstly you will make a string s which is pattern, hash and your input string from which you need to match. When you have made this string, you will apply your KMP algorithm, you will get this LPS array. Again, I'll explain how this entire thing is done, but when you have got this LPS array, your main task is to match your entire pattern with the string s. So you will go and start searching for this length of 4 starting from here. You will start searching for this length. Okay, have I found a 4? 4. Yeah, 4 I have found. If 4 I have found, which means ending at this location, I have a suffix of length 4. Because this says length and this is the suffix. I have a suffix of length 4 which matches with me. Now bhaiya, but if you remembered in the question, I was asking for, okay, if I have a OC, so I need the first index, which means I need the index 0 for O, which means if I have a TX, so I needed the index 2 for it. So although you right now are telling me this index, but I wanted this index right here. So how will I get it? As simple as that. You just simply remember one thing. If this is the index I, you know the length is 4, so you can just simply reach to I minus length, which is the length of your pattern, which means p dot size. That is simple. You will reach this index. But if you remembered one thing, this is joined. This is a joined s. So for sure, if this is a joined s, so you will have to also subtract this portion. Right, and that is how I'll show you in the end. You will just simply be subtracting my minus p dot size again. I'll show you by actually indexing itself, but right now it's just so as to know that okay, this is how you can match your pattern with your string. Ultimately, you will make your LPS array. When it is made, you will start searching for the p dot size starting from this value, which is at the index after your hash, and you know that hash is at index I is equals to p dot size. It is indexed at the index p dot size. You start searching for it. If you find any LPS value which is exactly equal, you will simply say, okay, I have found one match. And this is one match, but in this problem, I have to find all the matches. Now comes the interesting part. Let's see how we actually build this LPS array. Again, make sure that you stay with me. And if not, then you can just repeat the video itself. But we just got to know that in black box, even if we have the code right here, we simply know how to use that code. But now we will see how to actually use and how to actually build the LPS array. And then ultimately we will see the time complexity also for that. So firstly, again, considering you always remember the concept. Concept is longest prefix which matches my suffix. Again, you will see both prefix and suffix are same, so for sure there is no suffix at all here. So I have a prefix of a, no suffix here, so for sure initially it's 0. Now comes the first character. Again, this I indicates that I will iterate on all the characters one by one, and for every of the index, which means if I am at the index 1, I will be finding out the LPS value. That is my ultimate aim. And while we are discussing, we'll actually keep on building the formula also. So now this A says, okay, I am here, my A is here. I need to know the longest prefix which matches me. Now, for sure, I am at this index. So what all values I have right now? Again, if I am at this index, what all values I have right now? I have my current index, which is actually 1. I have my previous index, which is actually equal to 0, right? I have my previous LPS value also. These all values I have with me right now. So right now, logically, it doesn't make any sense to use anything. So what I can easily say, okay, right now I cannot understand anything. So I can easily say that, okay, if my I is here, and then if my I is here, then I know only that I am at index 1, so I can either go to my previous index, because I'm just trying to build the formula itself for KMP. So for building a formula, you need to know what all values you can actually use. So for that, you need to know what all values you have right now. You have the previous index, which means, and again, you want to build your answer as like with the as least complexity as possible. So you will only try to use your previous index. So you can use either your previous index, which is I minus 1, or you can use, okay, if I know that this value, which means of my previous index, what is the LPS value I had, maybe I can use that also. This is what options I have. Again, we don't know what options we have, but maybe these options we have, and maybe we can use that. But right now we don't know anything. So but by logic, we know that, okay, we have one of the prefix same as my suffix, so my value is 1. I am just building my answer right now. I don't derive any formulas right now. I don't know anything, so I just simply moved on. Then I am at this index right now. Okay, again, for B, I will just still have to figure out something, that what answer should B get. Now here, when I was making my A, I could make an assumption that, okay, if my S of I is actually equal to my S of previous index, which means if this current index and in this previous index, if both are same, which means I can actually match them, and I can add a 1 for them. Both are same, so my suffix and prefix are matching. Maybe I can infer this. Again, that is also not true. Maybe it is useful, maybe not. Which is, we have inferred, and maybe that is useful. Now, what if I am at this index? So if I am at this index, I can go to my previous index. Now, okay, if as you were going earlier, that you can go to your previous index, but if it doesn't match, because yeah, it is not matching. If it is not matching, then you will try to go on to some other index. How to know what other index to go? You will say, okay, what is my parent actual index, which is actually 1. So this will go previous index minus 1, and then it will go to previous index. Bhaiya, what you said, I didn't understand anything. Yeah, again, that is not for you to understand at all. It's just to showcase that, okay, right now, and again, right now I'm just building my pattern LPS array. The main part or the main crux will start when I'll start building my actual string LPS array. But with this, you would have seen, okay, if I am at index I just go on to my previous index. if it is not matching, then I'll try to go on and move backwards. How we move backwards? This length indicates how much I am matching with my previous part. So I know I'm matching one with my previous part. So this length will indicate I'm matching 1 with my previous part. 1, which means, okay, 1 length. So if I go on to index as 1 and then I subtract -1 from it, so I'll reach on to an index for that specific length. So that is the reason, if this LPS array represents my length, so I will have to go on to my actual index, then, which means this previous index, which is actually the length itself right now. Again, that can be confusing, but as soon as we'll pass this hash, it will start making sense to you. Right now, I'm just trying to make you build. Let's say if in future you forget how LPS array is even built, then still you will be able to still figure out how to actually build. That's the reason I'm just starting. I'm just without even making you know anything, I'm just starting to let you know that, okay, this is how we can actually think of, without even like knowing how intuition is actually working. So okay, we have this previous index which actually represents the length. So length will actually say that, okay, if I go on to my current actual index, if I do a -1, I will land on to the actual length which this was representing. So okay, I land onto here, but this is index, but I wanted my LPS value, so I again will go to my LPS. So this is how movement can look like between my pointers. Cool. Now let's skip all these part. So here you saw that I will have a 0. Here A is matching my A1, so I will have a 1. Hash is matching with nothing, so for sure it's a 0. Now comes the actual part, which means now your A is here. Now your A is here. Now you will have to start matching. So you will now actually start building your LPS array. Now for this, as simple as that. Firstly, you are at index A. You are at index 5. I is equals to 5. Right? Now, firstly, you will try to get bro. Now, if I say you, bro, if you understand DP very normally, then if I ask you longest increasing subsequence. So if you are at index I, then to know the number of longest increasing subsequences or longest increasing subsequence, you go on to all the previous indexes. Right? Now, if I say you that you have to anyhow do it in O of n. So in mostly DP, when you have to do it in O of n, you just try to access the previous index only, right? That is what you do. Okay, from the previous index, if I can figure out something. So that is what I will do. I know that, okay, I cannot do in O of n square. I can only access my previous index. So what I will do is I will access my previous index. Now that previous index, it can be your this value, which is 4, but again, your actual lengths are stored in LPS, right? This indexing are just for movements, but how much to move is stored in LPS. So you will go on to your I-1 so as to get to the value, but you know the length, how much my previous part has been matching, is actually stored in LPS. So you will just do a LPS of I-1. Then you will go on to this value. This will say, bro, my prefix, he will say, bro. See, what I'm doing right now is I have to just figure out, this is my string right now, which I have built. I am at this index. I am saying, bro, I need to know how much suffix is matching with my prefix. So to know how much suffix is matching with my prefix, I'll just go and ask my bro, how much do you think you could have matched? If you think that you could have matched properly, which means if my prefix, which means if I am at I, if I-1 would have matched properly, I would have known, okay bro, I know that you match properly. Then if where you match, which means if your length is 3, if bro you match properly, again bro, which means A will ask his previous bro, do you match properly? I-1, do you match properly? Bro will say, yeah bro, I match properly. And also this bro will say, bro, I match properly with the length of 3. Length of 3 is my suffix length which I am matching. So I'll say, okay bro, what I'll do right now is I'll go and check for the length of 3 in my prefix, and then after this length of 3, if the character which is there is matching with me, then for sure I will also match. I will also match entirely, right? This is the concept. So ultimately, my A will go and ask my previous bro, tell me how much suffix you are matching of length. He will give him the length. Now length is stored in my LPS array. From this LPS, I will go and directly try to say, okay, bro, I already know length 3 is already matching. Now this LPS length, which is 3, it will start pointing to index 3. Now index 3 will say 0, 1 and 2. 0, 1 and 2 is already matching. 0, 1 and 2 is already matching. So this length 3 is also working as an index for me. That this length 3, I'll go and point it to my index, which is this specific index 3. Now this will say, bro, you should compare your A character. You should compare your A character with this value, which means the previous index value. This was your previous index, which is actually nothing but your LPS of I minus 1. I minus 1, this is the LPS value. So now you have got the LPS value, which is the previous index. Now this will say, this will go and actually point it to a index. Now this index right here will show, okay, it is a third element. It is a third index element. Now third index element actually means that I have completed 3 elements. 3 elements completed. So this hit 2 targets, indicating that 3 length is done. 3 length is done, and now you have to check for the third, which means the 4th element. You have to check at the index 3. You have to check for the 4th element, and this is, I will just directly compare with this element, ith element. So I'll say if my s of I is actually equal to, S of my previous index, because you know this is a previous index. This is pointing to here. If this is equal, bro, well done, bro, well done. So I know that, okay, I know I can increase my length, but bhaiya, how much increase the length? You know that the earlier length was 3, which was saying by prefix index, which was saying by previous index. Again, previous index was working as 2 things. It is saying the length also. So this previous index is saying me that the length is actually a 3. Length is actually a 3 right now. If the length is 3, I know the length was a, sorry, change the color. I know the length was a 3, which was indicated by the previous index, because it is a LPS value. Remember, it is a LPS value. So it is saying that, okay, previous index is actually a, let's say previous IDX is actually a 3. Then I'll simply say if the S of I is matching with my S of previous index, then I'll add a +1. And that's how I can simply say now the length will actually become a 4. So this length will actually say now the LPS value is a 4, which means longest prefix which matches suffix is actually a 4 length. This is the entire funda of my KMP algorithm. Now coming on back again, you might say, bhaiya, this is a simple line of code, then this is a 3 line of code, then I'm done. No while loop, nothing else. I'll just simply check and I'll simply add. I'll simply write this condition same as that. Hold on, we have not completely iterated it. Let's see what catches we can actually encounter. So you saw that, okay, if you are at index 5, you will go and try to check for your previous value, which will say, okay, for me, bro will have the maximum suffix, which my bro has calculated already. Now, bro, maximum suffix, which bro has calculated, will be stored in its LPS of I minus 1. I'll go on to its LPS, and that I'll store in my previous index as a variable. Then this will say me, okay, length of 0 is matching for my bro. For my bro, length of 0 is matching. So I'll go on to my index 0, which will ultimately say, okay, 0 length was matching, which means nothing was matching. So I'll just compare, okay, if this S of I is matching with my S of previous index. Remember, this was a previous index. You just try to go here, saying now I can compare this, okay. Matching thing is 0, of length 0. Matching thing is of length 0, but compare this index 0 with my index I, which is 5. Yeah, bro, it is matching. At least this is matching, so for sure my length can be 1. My length can be 1. Matching length can be 1. So you will remember. So you will remember your this part plus 1 part was S of I if it is actually equal to your S of previous index. Now this part you saw actually became 0. His was equal, so you actually encountered a 1. Now you have got a much more intuition into it. Let's go on and do much further. Now I am at this index. So I'll simply ask my bro will go backwards and will ask bro, because previous will store what is the maximum suffix for my previous bro. So previous bro will say, bro, my maximum suffix which I was matching with the prefix was a 1. As you could already see, it was matching just a 1. So bro will say, bro, I was matching a 1. So my previous index became a 1. Now this one, as I already told you, it is working two conditions. One thing is it is matching your length, saying my bro was matching a length of 1. How did balloon come in? My bro was matching a length of 1. That was the first thing which he was saying. Other thing which actually infer is matching a length of 1. Now I can check for the index of 1, because index of 0 will indicate, okay, it's a length of 1. So I know it's a previous index. So I will go on to that index. This index will say ultimately that, okay, I need to now check for this previous index with this current index. I'll check, and ultimately it's also saying parallel that, okay, my previous bro was matching a length of 1 with you. So if I am matching with you, I'll increase my length. So he will say, okay, s of I is actually matching with s of my previous index. Previous index is 1. This index, it's matching. Yeah, A is matching with A. Bro, he will say, bro, I'm super happy because you computed the answer. This prefix index computed the answer, saying, okay, length is 1. I am also matching. So if I'm matching, I'll add a 1 for me, and whatsoever you have got as the LPS array, I'll add in me. So he will just say, bro, I was matching with you, so your LPS of I minus 1 of those previous index. So I'll simply, in your previous index, I'll simply say, if I was matching with this previous index value, which is I, s of I is matching with the s of previous index, I'll simply add a 1. So I've got a 2 here. 1 for my bro and 1 for me as matching. Again, let's go on much further. Now I am at B. Firstly, I'll simply ask my bro. Bro is simple. Bro is simply back to me, saying how much long suffix was matching with the prefix. Bro will say, bro, I was matching a length of 2. So now I'll assign my previous index as a 2. So as you have known so far, your previous index has been a LPS of I minus 1. This is your previous index in the very beginning. Now my bro will go and ask. So I know that AA was a biggest suffix which was matching for my previous bros. So I know the length is 2. Length is 2, which means I can now try for the index of 2. Index of 2, which index of 2 simply means that length of 2 is already matching. Try for the index of 2. So I know that, okay, length, this bottom thing is a length, but again it is functioning as two things, indexing also for to compare with the previous values. So I know one thing now so far, that I'll compare with this 2 index. I'll go on to this index value, 2 in value. Oh, B, it is same as B. Arey bro, wallah. Matching, bro, matching. Bro, matching. Okay, simply add a 1 for in the previous length. Previous length was 2. Simply add a 1. That's great. Bhaiya, it is so simple. We are simply checking my previous index value. If we are matching with it, then we are simply adding a 1. Bhaiya, what if it doesn't match? We will see that. That's the most important part. But okay, let's say we are at this I, specifically I. Now firstly, this I will ask and check his bro. Bro will be just backwards. Bro will say, bro, my maximum length was 3, which means my 3 length was matching. So you should try and check for index 3 if it is matching with you or not. So my previous index will actually become a 3. I'll go and check for the index 3. Index 3 again. Index 3 will say I have a length of 3 matching. Check for the index 3 now. Now index 3 will say, bro, are you matching with me? A and A. Yeah, bro, I'm matching. Okay, add a 1 for me. Add a 1 for the matching, and 3 is for the previous index. So far the story was so good, so understandable, right? Cool. Now comes the interesting part. Now you are at A. You will ask your bro, how much you are matching? Bro will say, bro, I am matching a 4. So matching a 4, which means length of 4 is matching for my bro, which is the previous value, which means the 4 length suffix is matching with the prefix for my previous. So let's go and check. So I'll just have a previous index. It will go and check for the index 4. This was a hash. This is now not matching with the A. This is now not matching with my A. Now, bro, what to do? Bro will say, bro, simply, if it is not matching with your A, simply this, okay, you can try for this value. Now it is not matching, which means, but bro, what it actually meant? This actually meant that this length 4 was matching with your previous bro, as you can see. So you try to check for this specific value so that it matches with you also, but it didn't match. It didn't match. So for sure, now your matching portion has become something like this, right? Now you will ask him, okay, I was at index 4. I'll go and ask him, bro, what is the longest length which you were matching? So he will say that at index 4, he will say the longest length which I was matching. You should not be concerned about it. You should be concerned about my previous value. So because here you was concerned about the previous value. Here, when you were computing the answer for this I, you were doing a -1 because your previous bro was actually storing the answer. So when I went here, I asked my bro, bro, what is the value? Bro, I did not match. You know one thing, okay, for sure, my 4, it did not match with my hash. I have to go somewhere else. I'll simply go backwards as I have been going here itself. Now, if I go backwards, here you remember, as you went backwards, you did not land it onto this. You were concerned about the length which was matching in your prefix. So again, same way, I went backwards, I did a previous index -1, but I am concerned about the length which is matching. So I went on down and checked for the length for this previous index -1. So I landed onto this previous index. I checked, it was matching. No, it was not matching. Then I went on to my previous value, which is previous index -1. But whenever we go previous, we always go and check the LPS. LPS is storing the length, how much length is matching. So length matching is actually saying 1, which means now I am saying for sure. Now I am saying for sure, bro, for sure. Hold on. For sure, you are matching a length of 1. For sure, bro, you are matching a length of 1. So I will say now assign this to previous index. Now again the same thing will continue. This will go on and check for the 1. Now bhaiya, what is this? It is so confusing. No worries. This actually means that so far my earlier I was saying that okay, my length of 4 was matching, right? But I figured out, okay, if the length of 4 was matching, then I cannot solve it. So I went on the index 4 and this told me that okay, I'm not matching. If anything is not matching, I go on to my previous index. But previous index should tell me how much length is matching. Okay, to know how much length is matching, I went on to this LPS value. Okay, I went on to its LPS value. Now LPS value says, okay, matching length is 1. And you can also see matching length for my prefix so far is 1. I am at this index. I am at this index right here. So matching length for my prefix is actually 1. So I can now repeat the same process for my, it is my matching length is 1. So just go and check for the index of 1 if it is matching or not. Index of 1, which is the previous index right now, its value is matching with S of I. Yeah, it is matching. If it is matching, okay, I will simply add a 1. Matching for matching, add a 1, and this is the previous index. But bhaiya, what this previous index says? This says that you have a 1 prefix length which is actually matching. You will see it is actually saying 1 prefix length is actually matching for you. That's the reason why you compared index 1, because you knew that 1 length is actually matching for you at this point. That is the reason. It is the entire, your LPS array works as 2 things: to know the length and also to know where to go on if we encounter something different. That is the reason. This is the entire crux of this. So firstly, if I just do a quick recap, what is the entire thing which you have to do? So you are at index I. You will firstly go and check for your previous bro, which means I -1. Bro, what is the length you have so far? So you will just go check for your previous bro, but previous bro's length you will check, and that you will store in your previous index. Okay, this previous index is now storing the length which my previous bro was actually matching. Now when this is done, I will have to go and check for this, I'll have to go and check. Okay, for this length 4, I'll have to go and check if S of I is actually matching with my S of previous index. S of I, this is S of I, S of previous index is this. If it is matching or not. Until it is not matching, which means until it is not matching, you have to keep on going and moving your previous index. How? Simply reduce your previous index value, because you will simply check and go and ask for his previous bro. Okay, he will ask his previous bro, but again, his previous bro, whatever we ask to previous bros is always the length of the previous bros. Remember, whatever we ask for the previous bro, we ask the length always. So previous bro, he went on, but he will have to go and ask for the length. Okay, so previous bro is, okay, this was the previous index, so previous bro to him is actually previous index minus 1, but whenever we go to our previous bros, we always make sure we ask for its length. So we'll ask for its LPS, and then my previous bro will say, okay bro, my length is actually a 1, which ultimately will say, okay, one length is matching for my bro. So if it is matching, then I can simply compare my this is my new previous index, That's the reason I'm simply assigning this to my new previous index, and I'll keep on moving backwards until my bro says, bro, I'm matching. So now here it will say my previous index is actually matching with my S of I. And that's how you will just keep on moving your previous index. Ultimately, when you have found out, which means when your S of I is actually equal to your S of previous index, which means, bro, matching. Okay, for matching, add a 1. And whatsoever length my previous bro would have been computed, because it will be storing in my previous index. Again, I'm mentioning a lot on this point that previous index stores 2 informations. One is the length, and also other is the at which index I should go on to next so as to match my string. So with this short and simple code, you can actually solve it. I have seen many people just putting a very big code, but this is the only code which you want to actually build your entire LPS array. That's it. Again, this is not an easy algorithm to study. It is actually, I have seen many people, they in an interview also, they might know the concept, but it is very hard to come up with the actual algorithm. Again, this is not an easy algorithm. I'm saying that out loud. Now, ultimately we have reached the super end, and let's say I is here. So firstly I'll go and check my previous bro. Previous bro will say, bro, length is 2. So length is 2, which means length is 2 here. So I can go on and check for the index of 2. Index of 2 is actually matching with me, add a 1, and previous index will actually show this value. And that's how you can simply solve it. Again, the code is pretty short and simple. I will have my string S. Remember, the best approach to actually find the longest prefix, which is equal to suffix, is by you have your pattern here, apply a hash in between, and then your main string in which you want to find this pattern. So anyway, if you find the length of 3, which means this was the pattern length, you find that in your string, okay, it is matching here, so the entire pattern, wherever the length is matching, okay, the length is 3 here, 3 here, and 3 here, it indicates my entire pattern is actually matching here. So again, this length, let's say it is actually n, this length, let's say, is actually m. So my entire algorithm will say the time is actually O of n plus m. And again, bhaiya, how it is possible, we will see that entire thing, but my space is actually O of n plus m also. But bhaiya, what if like my pattern is small and my string is large? So you will like, you have seen that you are only concerned about this pattern, right? Because the maximum match can only be in this range, because as soon as hash will come, it will restrict any matches any further. So the maximum match can be here itself. So this LPS array, you can only store for this n. So it can reduce to O of n itself. That is how the matching can be reduced, right? You can only store the pattern length, because that LPS of pattern only is required for you to actually build this entire matching. Now, coming on back to the code. Again, the code is as short and simple. Again, I'll highly recommend, if you have not understood it, please go and watch the explanation entire again, and especially for the part where we actually build the intuition of how the things work, how the matching actually works. Now, as I showed you, I will firstly make my LPS vector, which is this entire whole vector I need to populate. Right, I usually have this entire vector with me. Then as I showed you, for the LPS of 0, it is actually always a 0. LPS of 0 is always a 0. 0 is always a 0. I will start from the index 1 up till the super end. So I will start from the index 1 up till the super end. And these 3 steps only I showed you. These 3 steps exactly same. LPS, I'll go on to my previous bro. I'll ask my previous bro for its maximum length, maximum suffix which matches his prefix, which means I'll go and ask my previous bro. Now this will give me the maximum length, so as to just let me know that where I have to move on. I will say, okay, is it matching? If it is matching, if my SFI is matching with my SF previous index, then I can simply go on and come here. But if it is not matching, which means I have to see, if it is not matching, which means I have to do something like this, which we did here. Right, which we, if you remembered, we did here itself. So we have to keep on going backwards. So what I'll do is, if I am not matching with what my previous bro suggested to match, if I'm not matching with him, then I'll go and ask my bro's previous bro, get the length from him, and then assign to my previous index, and then again go and check the same thing. And I'll keep on doing until my previous index is more than equal to 0, more than 0. And as soon as any of the conditions goes false, I'll simply come down here. So this will say my previous bro was matching this specific length, which is the previous index. And if I am also matching with the length, I'll simply add a 1, else I'll simply add a 0. And this is the only short and simple code which you need to have for your KMP. Ultimately, you can simply return the LPS length, which will simply say you that, okay, this is the LPS length for you, which is the simple, this entire vector, this entire LPS vector. Now, the time is actually O of n plus m, where n is the pattern length and m is the string length, right? And space is also, right now for the code which I have written, is actually O of n plus m, because you are building the entire S string size LPS array. But as I showed you, you can also only maintain, your pattern LPS. Pattern LPS is the only thing which you are required, because you know that, okay, your pattern can never exceed, your LPS can never exceed this particular hash. So the space can be reduced to O of n. But now you will say, Bhaiya, why is this time O of n plus m? Because I saw this was a O of n. You will have a while loop which can also be O of n. So it should be O of n square, right? That is the entire special part about KMP. This is not. If you go back and look for how your actual LPS array is built, see, you are increasing your LPS array, okay, it is increased by 1, it is increased by 1, it is increased by 1. For sure, it is a length, right? It is the longest prefix which matches suffix. So it is a length. Length can only increase 1, which means if I am at this index, if my prefix matching with my suffix is actually of length 3, if I add myself, I cannot directly increase my length to 5. I will, okay, if I add 1 character, for sure, my length will at max increase by 1. So I can add max increase to a length of 4. So I know that the length increase are actually gradual. Okay, length increase are gradual, right? Okay, length increase are gradual. And we also know that, okay, for length increase, I just simply know one thing. I can simply need one pass. Like I simply need to go, okay, if I am at this, I'll go and ask my previous bro, his value is 2. So I'll just simply go and ask for the index of 2. It's matching. Yeah, it is matching. So for sure, I will simply add a +1 to my bro. So I know I'll simply add a +1. So my increments are always a +1. That is one thing. So I always know, okay, for incrementing, and bhaiya, how incrementing? For incrementing, I just need a 1 pass. You will see, I just went back, and for backwards, I just simply go and checked for it, this value. And if it is matching, then only I will increase. This is how an increase will work. Again, for increase, I will just simply be doing one step here and one step here. Only if this is matching. Again, I cannot go any backwards. Only if this is matching, I will actually be able to increase. So one back and then one checking that particular length. This is the only operation. If this is matching, Stop right now. Only then you can increase. If you go any backwards from here, now if I just go here, so you saw, okay, if it is matching, in matching, when things are matching, when things are going well, things are increasing, I just need one match, that's it. But if you will see at this point, increase was actually 1 1 1, but decrease can be any. It can actually become a 0 abruptly. But remember, if it becomes 0 abruptly, still it will increase gradually only. We saw that increasing can only be done gradually. So right now you saw that it decreased abruptly to a 2 value, which can always for sure happen, because you saw that, okay, we went on to a 4, it did not match, so we went on backwards, we then went on to the length, and then we again went on to a index of 1 to actually again start matching. So for sure I can go anytime backwards, which means this decrease can be anything. But if it decrease anything, still if we have planned to increase in future, it will increase gradually. So we can plot this as a graph. We know, let's say these are the alphabets which I'm doing, and I'm increasing gradually. 1 2 3 4. It decreased drastically, okay, 2, and then increased gradually. So I know that this length is actually a n, right? So for sure this length is actually a n. So for sure I can go and increase gradually. Okay, bhaiya, what if everything is increasing? Okay, if everything have been increasing, you for sure would have known that the complexity would have been just O of n, because you know that, okay, at every increase you are just doing a one pass, like one jump, that's it. But for decrease, that's the thing, right? For a decrease, you might end up doing any number of jumps. So for decrease, you might say, okay, bhaiya, for decrease actually that complexity will actually be more. I'll say no. Why? Because if you are at a 4, the maximum decrease which you can have is up till a point of 2. Oh, sorry. If you are at a 4, the maximum decrease you can have is up till a point of 0 maximum decrease. But if you have to again start decreasing, you will have to first increase, and increasing will come gradually. So you know, okay, if you have, okay, you have decreased to 2 here, which means you have used, let's say, 2 operations. You use 2 operations to decrease 2, right? To again, let's say if you want to again decrease, you will keep on increasing. You increase to 3. Right now the upper limit to actually decrease is a 3 itself. So you can decrease 3, like you can decrease just thrice to actually bring it to a 0. So you saw here that your decrease is bounded by your increase. So how much you have increased, that much only you can decrease. So ultimately you saw I can only decrease 2 here. I can only decrease a 3 here. That is a limit. That's a limit, which means, okay, I only decreased a 2 here. I can decrease a 3 here. Now this is the same way. You saw I increased 4 times, I increased 1 time. That is how, if you increase, your decrease is bounded by your increase. How much you have increased, only that much you can actually decrease. And if you decreased, you actually have to increase, and that increase can only work in 1. And that is the reason. That is the only reason. If you have n positive steps, then you will have to take n negative steps, so that you can actually start taking n positive steps again. And the positive steps will only take 1 step at a time. Thus, your total steps, negative steps, will always be n itself, because they are bounded by the positive steps, and positive steps itself just take 1 step. This is the part which no one explains. I don't know why, but this is the main crux. Thus, the worst case complexity is actually O of 2n, which means if your string, let's say pattern is of size m, your string is of size n, so your worst case is O of 2n, right? Sorry, your pattern is of size n, because maximum backwards you can only go in pattern itself. So in the pattern you can go 2n backwards, and that is the entire reason why your time complexity is actually O of 2n. Now coming on back to our actual questions. Okay, now we can just simply go and apply a string matching on our this. How we'll do it? We'll simply, okay, we'll have a m hash and then ocmm. We have a oc hash ocmm. Right, when this we have a hash, we will for sure be having our entire vector. We will for sure having our entire vector. This entire vector of LPS vector which we made previously will just simply say me the values. Okay, for this it will simply go and build this array. Let's say 0, 1, 2, 3, 4, 5. So let's say I build the LPS here itself. So it will be a 0, 0, 0, 0, 1, and it will be a 1. That is your entire, that's your entire LPS array. For this, if I just go 0, 0, 0, it will be a 1, it will be a 2, it will be 0, 0. So that's entire LPS array. Now, here to get these vectors, so to get these values as 2 and 3, how will I get this? Okay, I know one thing, that okay, my pattern length is a 1, so I'll go and start searching in this range for the pattern length of 1. Okay, here I have found the 1, which is the pattern length. So shall I say my answer is 4? No, because you saw that answer, because this is the index of pattern, hash, and then string. But I wanted my index of only of string. So best thing, I just wanted the beginning. So I should remove this entire stuff here from here. So with this example, you might not understand because the length is actually of 1 itself. But if I go and look back here for this LPS, you will see, okay, the pattern length is of length 2. So you will search for a pattern length of 2. So you will be at this location, right? Let's erase this. You will be at this location. You will be at this location right here. Now you want to know the index. As you can see, the index is actually 0. But for this LPS array, the index is 0, 1, 2, 3, 4, 5, and 6. So you are at index I. You just want to know this index as a 0 as the answer. You know that it is matching of length of the prefix sum, but you want to know the actual final answer. So you can just simply say, okay, the length is 2. So if I do a I minus length, so I can for sure reach to this value, right? So this is a I minus 2. 2 is nothing but the pattern size. Let's say PZ, pattern size. But remember, you have an extra length of 3. So ultimately, you wanted this specific index, right? You wanted to land onto this specific O because you saw this specific O. I am at 2. I actually want to land to a 0. But what is hampering me? This pattern itself, which I added of size 2, it is actually hampering me, right? So if I just subtract that, so I'll just reach on to my index 0, which is I minus PZ minus PZ. So I'll reach on I minus 2PZ. So this is actually, if I am at index I want to know the actual index in my original string. So I can just say I minus twice into pattern.size will be my actual index. This will give me a 0. Now, when I have got all these values, I simply know one thing, okay, if I have a 2, I need to do a binary search in my vector of B, which means the LPS array of B, and find the closest number. So I'll do a lower bound and I will just land on to my number 3. But as I said, when you ever, if this is the value I, this is the value j, if you want I minus j to be less than or equal to k, you always try to find both higher and lower values because it's an absolute number, right? So I'll just go and try, okay, for 2, lower bound is a 3, but then try for a smaller value also. Okay, I also try for a just one pointer behind my lower bound. So I'll try for a 1 also. With this, I'll just simply say, okay, this is a j, this is a j minus 1. So for sure, I'll try for both of them, 2 minus 1 and 2 minus 3. Any one of them, if it is less than equals to mod. If it is less than equal to k, then I am good to include my 2. And the same way I will do this for my number 7. I'll go and do bind search. I'll land on to my 8. I'll also try with the value of 4. I'll try for both the values and then I'll just say. But bhaiya, why both the values? As simple the answer. If this was a 6 and this was a, let's say, 12. Right? So you would have tried for 7 and 12, but you would have never tried for 7 and 6. So that's the reason. Try for the both nearest value to a number is actually important. And with this, if it is matching, then okay, it's good. So it's a combination of binary search plus KMP. The code is actually pretty simple. As you can see, firstly, I just copy pasted the entire same code of KMP. It's just that before even calling KMP, I'll combine my pattern, hash, and then string, and then call the KMP for that, and then get the vector, and then use the vector to know at what locations my pattern was matching. Again, for what locations I'll do, if I am matching, if my LPS of I is actually equal to my pattern or size, which means, okay, right now my pattern is matching for my LPS vector, and to know the actual index in my string S, I will use I minus 2 into pattern dot size. So I will firstly make my SA and SB, just combining A hash and then string, B hash and string. My vector A and vector B are just my vectors. As you can see, my vector A and vector B are my vectors. These vectors are my these vectors. Vector A and vector B are my these vectors. Location, actual location vectors. Right now, I will get my answer in my vector V for my KMP. So this is the LPS. This V is the LPS vector. Right, so this will contain the answer. V will contain the answer. I can start off from a dot size because I know that pattern. I know. See, why I'm starting from a dot size is I know one thing, that if I have something like this, so my pattern itself will start off from here. So I can either start from here itself or I can start from here itself. Although you can start from here itself also. No worries on that part. You can start from anywhere itself. Cool. So, but to just say I just start from a dot size, and then ultimately I just check that element, that specific element, and this element will actually say me that LPS length. LPS length is this element. If this is equal to my a dot size, which is the pattern dot size, then simply find the actual ID, find the actual index in my string S, which is I minus 2 into pattern dot size. If this is for sure more than equal to 0, then for sure push that in my valid index. So basically the valid index is where the pattern is matching my string, and the same will perform this operation for my vector B. Exact same thing. You can also make a function for this, but yeah, exact same thing here. Now when this portion is done, which means you have your VA and VB are the valid vectors. So this is a VA, this is a VA, this is a VB. When you have these valid vectors, then you are just good to start off and find, okay, iterate on your VA. For your VA value, for your VA of I, go and find the index B of I. But as I told you that B of I, okay, you will find the B of I value and will compute the absolute value. If it is less than equal to K, then you can push back your specific V of A of I, which is the index of pattern A. But you will also try for a smaller value. So if it is not equal to 0, then you will do a -1, which means just one index before. If this is less than equal to K, then you can just push this vector. So you will try for both the values. If this is okay, then simply continue. If not, then you will just try for this value also. And then ultimately you can simply return the answer. And that's how you can simply solve this by using bind search and KMP. I hope that you got it. Bye bye.